Hi everyone, I'm Jiaxin Xie. Today I'm going to represent the work I have done with Chen-Yang Lei, Zhuwen Li, Li-Aaron Li, and Qifeng Chen. It is video depth estimation by fusing flow-to-depth proposals. We want to build a system that, given a molecular input video like the upper one, and produce dense depth map video like the bottom one. Why we are interested in video depth estimation? With accurate molecular depth estimation, a mobile phone with a low-cost molecular camera can enable tremendous augmented reality applications without the need for dedicated depth sensors. For unmanned ground or aerial vehicles, depth estimation from a molecular camera can provide additional signals for navigation and obstacle avoidance. Molecular depth estimation is an active research topic as it can help billions of devices with a single camera see the world in 3D. In the previous work, supervised molecular methods mainly focused on single image setting, in which several works trained deep convolutional neural networks to directly regress raw pixels to depth value. The weight of CNN is updated by backpropagating the well-designed laws that calculate the distance between output depth and target depth. Nevertheless, this method has poor generalization ability, which means it is hard to use the model on unseen things. The poor generalization ability of supervised single image methods is inherent because they do not learn the physical laws that all data obey. What they learn is specific data distribution, so it is hard to improve this ability. And our work is fundamentally different from those approaches in that we take geometrical constraints between video frames into consideration, which is suitable for various data. Next, I will introduce the overall architecture of our proposed module, which consists of three critical components: the novel differentiable flow-to-depth layer, the camera pose refinement module, and the depth fusion network. The inputs of our framework are video frames or video frames along with the relative pose between frames acquired from GPS and IMU. In design architecture, arbitrary number of source frames is acceptable, and in our experiment, we take two source frames, one before the target frame and another after the target frame. These two source frames along with the target frame form the video frames triple for our training. For situations that only input video frames, we use visual odometry to get the initial pose between them. Otherwise, we directly read it from GPS and IMU. Then we estimate the optic flow from video frames. The forward flow represents the displacement between the target frame and before source frame, and the backward flow represents that for after source frame. Regarding optic flow estimation, we utilize the state-of-the-art optic flow method, FDNet. Note that we not only adopt the network architecture, but network weights and keep the trainable parameters fixed. Second, the initial pose and optic flows are fed into flow-to-depth layer to generate initial depth proposals and confidence map. Why call them initial ones? Because the quality of depth proposals is highly depends on the camera pose. The initial camera poses are not highly accurate, so the depth proposals and confidence maps computed from it are also not accurate. Then, the initial camera poses are refined by maximizing the sum of per pixel confidence in the pose refinement module. After it, we can get refined pose. Thirdly, we generated depth proposals and confidence maps with refined camera poses and the original optic flows through the flow-to-depth layer again. This time, the depth proposals and confidence map are more reliable. Finally, we obtain the final depth map by a depth fusion network that fuses given depth proposal, confidence maps, and the target frame. Hi everyone, and the first critical component of our network is the novel differentiable flow-to-depth layer. It takes optic flow and the camera pose as input and estimates rigid depth by triangulation in 3D. We can see in this triangulation figure, we get P and P prime corresponding pixel pair from optic flow and the projection matrix M prior from camera pose. This layer produces both depth proposals and confidence maps for the target frame by solving the epipolar geometry problem using a least square method. The least squares objective in the equation 2, we want to minimize the source frame reprojection error epsilon d. The difference between the traditional triangulation and ours is the objective function of traditional one includes reprojection error both in target and source frame. In our setting, we want to get depth of the target frame, so we assume the optimal P is perfectly in the range of target frame. The objective function only includes that in source frame. Then we can use least squares to get a closed form solution for optimal depth value, D star. The second component is post-refinement module. It takes initial poses and confidence maps as input and output refined poses. The initial relative camera pose may not be highly accurate due to noise sensor outputs from GPS and IMU or imperfect visual odometry algorithms. Since the flow-to-depth layer is differentiable, we can use it to backpropagate gradients from the confidence map to the initial camera pose and refine the initial camera pose by maximizing the sum of per pixel confidence, as shown in equation 4. Our experimental results show that the post-refinement module significantly improved performance. This figure shows depth proposal generated with and without post-refinement in two extreme examples. In the second row, without post-refinement, the initial camera pose produced poor depth proposals that have a vast region of negative depth. After post-refinement, in the third row, we can get depth proposals with higher confidence. The quantitative evaluation of this model will be introduced in the following ablation study part. The previous two components are differentiable but are not nullable, and the last component, depth fusion network, is a convolutional neural network that contains trainable parameters which is learnable. It fuses target frame, depth proposals, and confidence map as input and estimates the final depth map. There are two losses for updating network weights. The first is depth loss. This star is the ground truth depth map. D is our estimated one. This loss helps to train our fusion network which provides ground truth depth map in a supervised fashion. The second one is smooth loss. It helps to impose smoothness regularization on the output depth map. The final loss is the combination of these two losses. Lambda d here is 1, lambda s is 0.5. Regarding the network architecture, we adopt the single view depth network in SFM Learner. It is an encoder-decoder architecture with skip connections and multi-scale prediction. The detailed architecture can be found on our supplementary material. We conduct thorough experiments on molecular depth estimation and show that our approach produces more accurate depth maps than contemporary methods do. On the Kitty dataset, we train our model in the Eigen split and Huhosh split separately. This table shows our method outperforms state-of-the-art methods in both splits. And this figure illustrates some qualitative results on the Kitty dataset. Our method also achieved the best performance. Besides the outdoor Kitty dataset, we also conduct experiments on indoor ScanNet dataset. This table compares our method with two representative approaches on the ScanNet dataset. Our method performs better on the first 9 metrics and achieves comparable performance with Dawn on matrix data 3. This figure also shows the comparison on the ScanNet dataset. The first row shows depth maps and the second row shows error maps. Comparing the error maps, we produce depth map with lower error compared to Neural RGB and Dawn. Our output depth map is less noisy and more complete. In the very beginning, as said, the previous supervised molecular method had poor generalization ability, so we also designed experiments to evaluate our generalization ability. This table reports the quantitative result of cross-dataset evaluation on the Wemo dataset. Our model, trained on Kitty and tested on Wemo, suffers less performance degeneration than Neural RGB and Dawn in the cross-dataset evaluation, and completely surpass SFM Learner, which is trained on the Wemo dataset in an unsupervised way. These qualitative results suggest that our depth proposal can often preserve object boundary in the estimate depth map, even in cross-dataset experiments. Ablation study shows our camera pose refinement improves those metrics by about 3 to 6% and surpass naive baseline to a large extent. We conclude our contribution as follows. First, we present a novel framework with differentiable flow-to-depth layer for video depth estimation. The flow-to-depth layer refines camera pose and generates depth proposal by solving a triangulation problem between two frames. Second, a depth fusion network can merge the depth proposals from the flow-to-depth layer to produce the final depth maps. The depth fusion network can optionally take the depth map generated by other methods to improve performance further. Third, we conduct thorough experiments on molecular depth estimation and show that our approach produces more accurate depth maps than contemporary methods do. Our model also demonstrates stronger generalization ability across datasets.